All right, let's start with a little bit of background before we continue with these PE diagrams. One of the things I want you to remember is what happens during a chemical reaction. So this goes back all the way to first semester, that when we have a chemical reaction occur, bonds are broken and reformed in different ways. And since the energy in a reaction comes from the breaking and the forming of the new bonds, you can actually figure out the total change in energy for the reaction. And so that's what we're seeing happening in the potential energy diagram. So feel free to write down this information before we get started on the worksheet. I just want to make sure you understand what it is we are seeing in the potential energy diagrams. So here I have drawn two water molecules. If we look at these two water molecules, there are a total of 4 oxygen-hydrogen bonds. If I were to use a process called electrolysis, where you drive some electricity into the water, I could decompose the water and hydrogen gas into its separate components. When I put the water through this electrolysis, I'm adding energy into the system. So at that point, I now have an activated complex. I've had to add 1,868 kilojoules per mole. That's going to be the activation energy. That's how much energy I need in order to get this reaction going. So that's my activation energy, and I'm now activated. So the products that I have now have 2 hydrogen bonds and 1 double oxygen bond that forms. And so we have new products that have been made, new bonds that have been formed. And that process is going to require 1,362 kilojoules of energy. So we needed energy to go in to break the bonds apart. And then energy was released when those bonds were reformed. And we can figure out what the total energy of the reaction is by looking at the energy you started with versus the energy at the end. And so we can calculate that, and we call that the delta H, or the amount of enthalpy of the whole overall reaction. So since it took 1,868 kilojoules per mole to go in and 1,362 kilojoules of energy to come out, we can see that the delta H of the reaction then is going to be 506 kilojoules per mole. So this means that the reaction absorbs more energy from the surroundings than it releases. And so this would be an endothermic reaction. So go ahead and load the Energy of Reactions worksheet. This is the worksheet we're going to go over today. So take a minute to fill in the definitions of some of the important words when it comes to the potential energy diagrams. So the chemical potential energy is that energy that is stored in the bonds of a substance. So on the previous slide, I was talking about the bonds that are in the water molecule and how those break apart. And we talked about on the previous slide that activation energy is needed, that we have to add some energy in. And in the process of breaking that water apart into its separate components for that electrolysis, the energy, we have to add in a certain amount of energy in order to get those reactants to break apart, to get those bonds to break apart, in order to get that reaction to actually react. And if we have an endothermic reaction, that endothermic reaction means that energy has to go into the overall reaction. Endothermic is also going to be when that breaking of bonds is occurring. So we saw that on the previous slide. If you have to go back, you'll see energy had to go in, and it was a positive enthalpy, or a positive amount of energy that had to go in order to break those bonds apart. And then finally, we have an exothermic reaction where we have energy being released. And so our delta H and our Q are both going to be negative during this. Exothermic changes are going to be when the new bonds are forming. So again, go back to the previous slide and you see that as I'm talking about the potential energy diagram. On all of these potential energy diagrams, we're going to do the same thing. For letter A, we are going to calculate the activation energy. The activation energy we can determine by looking at how much energy do the reactants begin with and how much energy is needed to get up to the activated complex. And so we're going to subtract those two. You can see my work in letter A here. So my activated complex is 150 kilocalories of energy for my activated complex, and my reactants started with 50 kilocalories. So activation energy, here's what you're doing. You're taking the energy of the activated complex and you're subtracting the energy of the reactants. So take a minute if you need to write down how you find that activation energy. The energy of the activated complex minus the energy of the reactants. Now, on all the problems for letter B, we're going to calculate the energy of the reaction, or our delta H. Our delta H is determined by taking our products, the energy of the products, and subtracting the energy of the reactants. So we are going to look at how much energy is in our products and how much energy is in our reactants, and we're going to subtract those, which you can see I did in letter B here. If I look at my products, it looks like I'm at about 100 kilocalories. So I take the energy of the products and I minus the energy of my reactants. So my amount of delta H, my energy of the reaction, is a positive 50 kilocalories per mole. Finally, for letter C on every problem, we're going to determine if it is exothermic or endothermic. This reaction would be endothermic. Our general rule that we can remember is that delta H is going to be positive when it's endothermic, and delta H is going to be negative when it is exothermic. Endothermic energy has to go in to the reaction, and exothermic energy has to go out. So you can see that if we look at our reactants here versus our products, we have more energy at the end. So energy had to have gone in, since we have more energy in our products than we do in our reactants. So we had to add energy in to get the energy up higher at the end than the amount of energy that we had at the beginning. I'm going to do the first problem with you first. So we're going to move on down to number 2. So remember, for A, we are calculating the activation energy. So to calculate that activation energy, we want to look at the energy of our reactants and the energy of the activated complex. So I've highlighted both of those in red. So in order to calculate this, we're going to do 500 minus 100. And to get up to be activated, we're going to need 400 kilocalories per mole of energy. So that's letter A. For letter B, I'm going to use a different color to highlight. For letter B, we need to find the energy of the reaction. So we're going to look at our product's energy and our reactant's energy. So for our delta H is found by taking the energy of the products minus the energy of the reactants. So it looks like my products have about 300 kilojoules per mole, and my reactants have 100. So this would be 200 kilocalories per mole for my delta H. Finally, we want to determine if this is exothermic or endothermic. So we're going to look at Do we have more energy or less energy than we did at the beginning versus the end? And our delta H is positive. So if our delta H is positive, this is endothermic. So go ahead and pause the video, and I would like you to try to do 3, 4, and 5 on your own, and then come back and check your answers here. So here are my answers to the first one. Our activation energy, we're starting at about 600 and we have to get up to about 1,000. So it's going to take about 400 kilocalories to get that energy, to get the activated complex going. Then our delta H is the difference between our products and reactants. So we start with our products, so 200 minus the 600 is going to give us a negative 400. So we're releasing energy, which means that we are exothermic, and we've got a negative delta H. For number 4, our activation energy, we're starting at about 25 for our reactants, and we've got to get all the way up to 200. So 200 minus the 25 means that we need 175 kilocalories per mole of energy to get up to that activated complex. Delta H is going to be the difference between our products and our reactants. So our products are at about 175 and our reactants are at 25. So that gives us a lot of energy going in to the reaction because we've got more energy at the end than at the beginning. So we have an endothermic reaction for number 4. And finally, on our last one, we have, we're starting, I would say this is at about 30 for our reactants. And to get up to our products, we have to get up to up to our activated complex, we have to get up to about 90. So we need a total of 60 kilocalories of energy here to get activated. Our next problem, we want to calculate our delta H. So we take our products, which I would say is at about 10, minus our reactants, which is at about 30, and so we get negative 20. So notice how energy is less at the end than at the beginning. So energy went out, and we are exothermic. So the last thing that you have to do for today is you need to click on the PE diagrams quiz. You can take it an unlimited number of times. You're going to be thrown 5 questions that you have to answer. Every time you take it, you're going to get a different set of 5 questions. You can take it as many times as you would like to in order to practice this. Have a good afternoon.